Hello, everyone. Welcome back. My name is Paula Teixeira, and I am the host of session number 7 that is beginning right now, the Orion Uncovered meeting. Before we begin, I'd like to remind the audience that you can ask questions in the YouTube chat window on the side. And we also have a Google Group forum, and so you're very welcome to continue the discussion offline there. We have our first speaker of the session already with us, so Josefa Kosciendo from the University of Vienna, and she will be talking about Orion A with Gaia DR2, how 3D changes everything. So it's all yours, Josefa.
Okay, thank you. So can you hear me? Yeah. Okay, then I start. So yeah. Welcome to my talk, and thank you for giving me the opportunity to present my work here. And today I'm going to talk about Orion A, which is not a surprise since it's an Orion meeting. And what I also will show is results from Gaia and how important it is to know things in 3D and not only in 2D projection as we did so far. And what you see here is a simple scatter plot of Gaia sources towards Orion A. So it's sources with parallax measurements in Gaia. And it's very nice that you can already see the high extinction regions of the cloud by simply making a scatter plot. So it's basically looks the same as like from Herschel, the dust emission. So this is the Orion A cloud as observed by Herschel. So when we look at it in more detail, so to give you some idea what I will talk about today. So what you see here is the whole Orion A cloud containing the Orion Nebula cluster, this part, and these regions are actually rather more predominantly low mass star-forming regions, and this is a high mass star-forming region. And when looking at this cloud in projection and assuming a distance of about 400 parsecs, the length of this structure would be 40 parsecs. And the nice thing about Orion A, of course, is that we have these two different environments and can start different things in star formation. And the two different environments get even more clear looking at different wavelengths. For example, in the near infrared, this is a ESO-VISTA infrared survey, the so-called Vienna survey in Orion or Vision, conducted by my colleague Stefan Meingast. And here we really see the H2 region around the ONC region and the very dark seeming dark clouds L1641 and L1647, which I will call the tail for simplicity. So, but what actually makes these two regions so different? Why do we have much more star formation on one end of the cloud compared to the other? Well, first, I thought I'd make a simple test to study this. And I looked at the gas mass distribution across the cloud, so the line mass across galactic longitudes. And what we found that actually the gas content across the cloud is actually rather constant. Of course, the volume density is likely higher at the ONC region, but the amount of gas that is available for star formation is not that much different. While which we already have heard from Tom McGath, that we have a higher peak of star formation rate at the location of the ONC. So we found by counting young stellar objects that there is a factor of 10 higher star formation rate from the head to tail. So I used about 3,000 YSOs for this test, and these were collected from Tom McGath and also by myself and various other works. So when we look at dust emission again, we again see that there's not so much difference while we observe this high peak of star formation rate. So why is that, and how well do we actually know this region? And do we actually know how this structure looks in the galaxy? How is it orientated and so on? And here we now have the great opportunity to use Gaia data. And what I did in a recent paper from last year, so I used Gaia DR2 on the YSOs that I showed before, which then left me about 700 YSOs with infrared access that have good parallaxes in Gaia. And we looked at distance variations along the cloud. So that means, in this case, along galactic longitudes. And I looked at variations within 1 degree bins along galactic longitudes to get an average, because you see here's rather large scatter, but you can see in both the scatter and at the average distances that indeed it's not a constant distance, but the tail seems to incline towards further distances. And also what Amy Stutz mentioned earlier today, there seems to be a wiggle structure at the ONC, but I will not go into detail about that today. And why we use YSOs as traces for the cloud is because, of course, they're still young. They formed in that cloud and they're still connected to the structure. And what we also know is that they share the same radial velocity as the cloud, as was, for example, shown by Alvaro Acar in 2016. So to give a better impression of this shape, I put it in equal aspect ratio, which is of course not, when you put Geelong versus distance, it's not a good impression. So here, what I did, I show galactic Cartesian coordinates. So he put the x-axis towards Orion A, and the y-axis then is coincidence with galactic longitudes. And now we really see that there's a high inclination of the tail, about 17 degrees. And that means then that the length of the cloud is actually twice as large as previously assumed. It's about 90 parsecs. Of course, now knowing this distance variations, this will also have implications on other observables, like when calculating cloud masses or binary separations. So we also want to know how is the cloud oriented within our galaxy. And to this end, I put these average positions I derived before into a galactic Cartesian coordinate space. And on the left, you see a top-down view, basically, in X and Y. And this is X versus Z and Y versus Z. And what is revealed here already, that the cloud actually seems to be oriented towards the galactic midplane, so it points up. This is not seen in projection. And also, this inclination actually here, it seems like the head seems to be bent with respect to the tail. So these things were not known before Gaia, and especially this peculiar structure of the head, it raises, of course, the question, how does it come to this structure? For example, one can speculate, was this gas pushed by some external process, for example? So these things have to be investigated, and there might also be further evidence for this theory, for example, in the velocities. So I also looked at the YSO's velocities. So to this end, I use proper motions from Gaia, and there are radial velocities from the Apogee survey from Kunkel 2018. And what you see here is the UVW velocities, which are the velocities in the XYZ space. And we see that in LSR velocities, the W and V actually are at 0 almost, while only the U velocity shows a radial velocity gradient, which is also observed in radial velocities from the gas. And to give an other view of this, I put it again in the 3D space. So this is the YSOs with the UVW velocities. And the vectors show the LSR velocity in this space. And especially in the X versus Y space, we see, so the sun basically looks from here towards the cloud. And the yellow is the head of the cloud, blue means the tail. And the velocity vectors at the head move further away from us than faster away from us than the tail. This can be seen a bit more clearly when I show relative motions, now relative to some average velocity within the cloud. And I color-coded it by the radial velocity. And you see that the head seems to be relatively redshifted compared to the tail. So can this also be a signature of some external event in the past that pushed this region? So now I want to look at the cloud's 3D space motion. And as I showed you before, so we have the YSO's motions in all 3 dimensions. But as I also mentioned, so we also have gas radial velocities. That is what you see here. So this is along galactic longitudes. The pixels are taken from the cloud region only. So this is a map of radial velocities from Nishimura 2015 from the 12th CO map. And I will only use this radial velocity information which is correlated to high extinction regions to get rid of any possible contamination from the surroundings. And that's what causes this rather narrow shape. And here on top, I already show you the YSOs and the average radial velocities of both. They agree very well with each other, which was already known. So to then infer on the cloud's motion, I will use YSOs, proper motions, and the gas radial velocities. And what you see here is these vertical lines are then bins that I chose as subregions, basically. So in the tail, I chose regions of constant radial velocity, which is also a very interesting signature that at some point there are like step-like structures in radial velocity, which
I did 1 minute.
Okay. And for the next analysis, I will exclude the NGC 1977 cluster. I think Konstantin Gateman will talk about this later because it has some peculiar motion with respect to the gas. So, and this is then my result. So I put these velocity and position informations into GalPy, so a Python package which uses a simple Milky Way potential. And I calculated the orbits back and forth in time, minus and plus 20 million years. And what you see here as dots in this Y versus Z plot, this is the position of the subregions that I showed you before here, where they are lying today in this plot. And these are the orbits 20 million years in the past and in the future. And what is interesting here is that Orion A obviously is at a Z minimum currently, and it will move up towards the plane in the future, which is also why the W velocity is 0 at the moment. So this is not equal aspect ratio. Actually, it looks like this. So when you put both axes in same dimensions. And at the very last, I show you a quick video. So this is again these subregions that are derived from the cloud. And here is again the Y versus Z, X versus Z, and the top-down view, X versus Y. So these are the orbits. That's how the cloud moves. I start in the past. Now it's -8, -7. This line gives you the direction towards the center of the galaxy. And what we see that the regions seem to shift their position around their orbits. So at the beginning, the head of the cloud seems to be closer to the galactic center, while when we go further, they seem to change positions, and also likely due to the fact that the radial velocities are high here, they seem almost to move apart from each other. Of course, this has large errors which are not shown here right now, and if you go further to the future or past, this will not be correct. And also, here are not any gravitational effects included, which might act between these parts. So I will leave you with my conclusions, since I think the time is over soon. What is most important, maybe, that we found signatures for external processes that might have acted on the cloud, which we can see maybe in the cloud shape and in the observed radial velocities, and also the very high star formation rate could be a signature, so that it was triggered due to some external process, like a cloud-cloud collision, or from previous generations of stars like supernovae or winds from the foreground population that was recently confirmed by Chen. Do I still have time, or?
No, that's it. Thank you very much.
Okay, then I will leave my conclusion and take some questions. Thank you.
Yeah, no, very nice talk. Thank you. We have questions from our audience. Marina Kunkel is asking about the Barnard's loop in the context of a possible progenitor for the external push. So any thoughts about that?
Yeah, we thought about if there was a supernova if it could still be observed, of course. I think the Barnard's loop, we looked into it quickly, but I think, I'm not sure about the age, but it might be too young even, but this has to be investigated. But it's a good question, because actually finding some remnant of a supernova would be also a confirmation of our theory in the end.
And she has one more question. Is the self-gravity accounted for in the traceback?
No, I think I mentioned it shortly. So this was a very simple test, but in the future, one should really also include self-gravity, of course, within the cloud, because otherwise, yeah, the traceback or calculating forwards would not be correct, I think. But also my idea was to actually see how the cloud itself moves as an object through the galaxy, even though the interaction between the subregions might be wrong yet. But I think it's very interesting that you can do this now by having Gaia and other information, yeah.
Very good. Well, thank you again. And I will remind everyone that we can continue our discussion on our Google Group forum and also in the chat window of YouTube. And we'll move on to the next speaker,
Okay.
which is Eleonora. Thank you. Which is Eleonora Zari from Leiden Observatory. Hello, Eleonora.
Hi, can you hear me?
Yes.
Yeah, good.
And so
Let's start.
Eleonora will be talking about the structure, kinematics, and ages of young stellar populations in the Orion region. So yours, go ahead.
Yeah, okay. Thank you. Can you hear me well? I hope so. I hope you can also hear me in the room. Okay, so I am a PhD student here in Leiden, and today I want to present you the results that we obtained in a paper that we published recently with Anthony and team about the Orion OB association. So I would like to start first with a quick introduction about OB associations. So in the figure on the slide, you can see an image of this COSEN OB association. COSEN is the closest OB association to the Sun, and is more or less directed towards the galactic center. So here you see all the blue bright stars belong to the OB associations. And indeed, OB associations were defined first as loose groups of young massive stars, not gravitationally bound. As you might know, COSEN is located next to Fucus, next to Lupus, next to the Pipe Nebula. So, and this is not, so it's located next to star-forming regions. And this is not a property only of COSEN, but also of all OB associations. And for this reason, OB associations can be considered as the context in which star formation happens, and if you want, the last stage of the massive star formation process. Although OB associations are studied since 1949, I think, there are still a lot of open questions. First of all, it's not really clear how OB associations are formed, what causes the distinction between open clusters and OB associations, and if more on the large scale, what are the properties of the ensemble of OB associations in the solar neighborhood and in our galaxy, and now those properties compare to what is observed in other galaxies. So the conference is about Orion, so now I'll go back to Orion. So here I'm showing you in this figure two plots of Orion in the optical and in the far infrared. I don't want to give a very long introduction about how many stellar complexes Orion contains. I just want you to, and you probably already know, that Orion has an OB association, and all the blue stars in the region are basically belonging to the association, or somehow they are related to the association. And I want also you to remember that Orion is a very complex region. There are a lot of clusters, and there is a lot of substructure in kinematics, in physical space, and in ages. So in this paper, we studied, we tried to answer the questions that you see, that you can read on the slide. So we tried to understand what is the structure of the association, what are the characteristics of the association in terms of ages and kinematics of the population, and how does that relate to theories of sequential star formation. And Gaia is the perfect data set to address these topics. Already in 2017, so 2 years ago, we did a study where we used Gaia DR1 photometry combined with 2MASS to study the distribution of the young stellar population in the sky, because parallaxes were available only for a small subset of sources. And we gave a first picture of the star formation history of the association. And one of the main plots of that paper is this one on the right-hand side of the slide, where you see that it looks like there is a young diffuse population of young stars loosely clustered around some well-known open clusters. So, for example, around 25 Ori, the belt population, Sigma, the ONC, and I will go back to this. So after 25th of April, it sounded interesting to continue this kind of study using this time Gaia DR2. And in this slide, I'm showing one of the first visualization that I made after DR2 came online. This is just a scatter plot of the sources in the Orion region, color-coded by BP minus RP. And you can already see that there are a lot of red diffuse sources, and these are young stars diffuse in the region, which already confirmed what we found in 2017. So now I want to go quickly to the data selection and then go to the results. So the way we selected the data is very simple and straightforward. So in Orion, it's very easy to see the pre-main sequence just by plotting a color magnitude diagram. And we use that to define these two isochrones that you can see on the left-hand side. And to select the population, this is a procedure that is quite common to select young stars. And you can see the stars in this band on the sky on the right-hand side of the plot. And again, you see the same structure as I showed a few slides before. And here I just highlighted the main region which we focus on in this study. So 25 Ori, the belt, Orion A, and up there, Lambda Ori. So the first thing we did after selecting the sources was to study their distribution in space. So okay, so on the right-hand side, there is, again, a sky plot. This is just for reference. The important result is on the left-hand side. This is a density map of the stars in the Orion region in galactic Cartesian coordinates. So you're all, in all the panels, you're looking at X at the X and Y plane. X is towards the galactic center, and Y is in the direction of galactic rotation. And the sun is always in 0, 0. So it's always around here, 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 and so on. And then the slices correspond to different heights with respect to the galactic plane. So this is low, and this is towards the plane. So, for example, the ONC is lower with respect to the plane than Lambda Ori, which is in the last 3 panels, which is higher towards the galactic plane. The one thing I want you to notice is that, for example, here, in the first top 3 panels, you see the ONC. In the first 2 panels, it's marked by the orange cross. And in the 3rd panel, you see that there is something that looks like it's in front of the ONC. It's in front and it's a bit above. So when you project it on the sky, you see that it is exactly in front of the ONC. Now, the tricky part is identifying the clusters. So yesterday we heard the talk by Bo-Kwon Chen, and I am assuming that now you're all experts about DB-scan. We also use DB-scan, and we applied DB-scan in only in space, so not considering the proper motions, but just considering Cartesian coordinates x, y, and z. We applied it twice. The first time, we set a very low threshold just to separate the population from the field stars. And we identified these 5 groups. The second time, we applied DB-scan only on group B, which is represented by the orange points, with a higher density threshold in order to separate structure that were visible just by a scatter plot of the points that were not separated after the first application of the DB-scan. So at the end, we end up with a number of groups. I think, I don't remember if it's 11 or 13. And for all these groups, we studied their kinematics and their ages. So here in this slide, of course, I don't plan to present all the ages and all the kinematic properties of all the groups, because that would be a bit too long, I think. I want just to give you an example of how do we do the age estimate and the kinematic analysis. So for the ages, we fit the isochrons to the groups identified by DB-scan. We estimate not only the age, but also the extinction values towards all the clusters. So in the figure, you see a two-dimensional likelihood where the likelihood has its maximum, then that is the most likely value for extinction and age. So for example, for this group, we found an age of 7.2 in log, so it's 15 million years, I think, and 0.3 of extinction in AV. For the kinematic part, we applied a code that we wrote in Python following Lindgren 2000. It was applied also in Reno 2018, Bravi 2018. And basically, we compute the velocities, the velocity dispersion, and when it's possible, the expansion coefficients of the single groups. In the figure, you're actually seeing a proper motion plot of the sources in the belt region. The gray sources, the gray points represent all the stars in the belt region, and the colored points represent all the members of a group identified by DB-scan. Again, here, the single values are not that important. What I want you to remember after this talk is that there is a lot of kinematic substructure, and this is a property that is very well visible in the belt, but it's also visible in other regions. And I think Yanez, after me, is going to talk about that in for 25 Ori, and also in Orion, towards Orion A. There is a lot of substructure.
Eleonora, you have 30 seconds.
I will be a bit longer, but I hope you don't mind. Just one slide more.
I will.
So this is the final plot that I wanted to show you, so don't worry. This is actually the most difficult plot, I think, of the presentation, but we will go through it. Again, this is a visualization of the density of sources in X, Y, and Z in the tree projection. The contours represent the source density, the Young source density. The arrows represent the velocities of the groups that we identified, and the arrows are color-coded by the ages of the groups. So when I first plotted, I had the idea of plotting these, I thought, oh yeah, we're gonna see a gradient, we're gonna see something, we're gonna see an age sequence. I don't think I see any age, clear age gradient. We see that there are old groups around 7.2 in log age, which means around 15 million years old, towards 25 Ori here, and also towards the belt. So our conclusion is that in Orion there is a lot of kinematic substructure. That star formation probably started in 25 Ori, and also in the belt region 15 million years ago or 20 million years ago, around more or less around that age. There is not a clear age gradient, I think, and this questions a bit sequential star formation scenarios. So we need to explain what we observe, and to explain what we observe, I think we need simulations, hydrodynamical simulations, similar to what Krause 2018 did. And also, I think from the data point of view, we need radial velocities, not just of the embedded population, but also of the dispersed young population. So with this, I thank you for your attention, and I'm happy to take questions.
Thank you, Leonora. That was a really interesting talk. I'm still waiting for questions from our online audience. Are there any questions in Leiden? Yeah, I have a question about these older clusters that you are finding. In terms of their spatial concentration, do you see any systematics, or are they as concentrated as the younger clusters in the region?
What do you mean by systematics?
I mean, is their spatial distribution, how distributed are they? Are they relaxed? Do you see that?
Well, they are, well, Lambda is very easy to separate from the rest of the population. The others are distributed towards, okay, they basically correspond to no clusters. So, for example, we do retrieve sigma Ori or 25 Ori or epsilon, or the population around epsilon Ori. We retrieve the Orion A population. So I call them groups or clusters, but many of them can be traced directly to known clusters in the region. It's just a way to classify them. It's not that they don't correspond to already known things. I don't know if I answered your question.
Yeah, that's good. We can continue discussion. I will pick your brain. Very good. Well, if there are no other questions, you can move on to the next speaker. Thank you again.
There is Joao.
There is? Okay.
Hi, Paul. I'd like to ask a question. So
yes, please do.
You broke the entire structure into 5 main structures?
Yeah, plus the belt, plus 25 Ori.
And then you took one of these structures and you broke it into substructures.
Yeah.
And this applies to all of us.
Yeah.
Vulcan, Shen,
I think,
where do you stop?
I think at the end, what we find is very similar. Yeah. And also the clusters that we find, I think it's very similar. Yeah, I don't know. I think at the end is an arbitrary decision. It would be nice to have another, a more like, not arbitrary criterion, but yeah.
Thank you.
Okay.
Thank you again. All right. So now we will hear from Yannis Kos. Hello, Yannis.
Yep.
So Yannis is from the University of Ljubljana, and we will be hearing about chemical abundances in the Orion Association. Please go ahead.
All right. Hi, everyone. So I'm interested in spectroscopy and galactic archaeology, and that's where the motivation for this talk or for this project that I'm going to present you comes from. So in galactic archaeology, there was this idea proposed a while ago that you can find stellar siblings that are long dispersed in the galaxy based on the chemical signatures. So most stars were born in clusters that were born from chemically homogeneous gas. And these chemical signatures are conserved throughout the life of the stars. However, this is a really tough goal of galactic archaeology. There are only few papers that show successful chemical tagging. Also, theoreticians tell us that indeed at least most clusters should be chemically homogeneous. That's something that's much harder to test in practice, as chemical abundances precise chemical abundances are hard to measure. But also, it would be cool to find some clusters that might not be chemically homogeneous. And Orion is an obvious choice because it's the most chaotic star-forming region among the nearby star-forming regions. So it has been proposed in the past that we might observe self-enrichment in the Orion complex. So we have clusters of different ages. So supernovas from older clusters might have chemically polluted the younger clusters. However, the data in the past wasn't sufficient to show anything like it. Like here in the bottom right, you have a picture how data from a decade ago looks like. Right now, we have more clusters than they have stars observed. So the first obvious choice is to make more observations, but of course, you also want to know what clusters you're observing. So this is my algorithm for finding clusters. Basically, I use NLink. It's a bit obscure algorithm to find clusters, but then I define sort of a sphere in 6 dimensions to actually constrain the members. I was only focused into these regions here on the right that are marked with green polygons. That's where I have spectroscopic observations. So I didn't bother to cluster Orion Nebula clusters or Sigma Orionis. But here I find 15 clusters. They're very similar to other clusters in the literature, so I think we agree fairly well in this respect. A bit more controversial are, if you want to see all of them, here's an animation in the middle. You have proper motions. Top right is parallax, bottom right are radial velocities. Obviously, if you do a spectroscopic survey, we have radial velocities as well. So yeah, 15 clusters. Nothing that special about this plot. A bit more controversial are ages. It's really hard to fit isochrones to HR diagrams. I think it's even harder to do it in a computer. So the way I do it is I fit isochrones by eye. Basically, there are 2 regions that are most sensitive to age. One is this pre-main sequence where the stars are falling down toward the 0-age main sequence. You see the cursor there? Oh, it's jumping around a bit, sorry. This is not very sensitive to reddening, which is great, but these are all dark stars, so the errors are a bit larger. Then there's another region here where the pre-main sequence merges with the 0-age main sequence. Very sensitive to absolute age, but also sensitive to reddening. However, reddening can somehow be constrained by these stars up here. But basically, in this way, we can get ages with precision of something like 10 or 20%, depending on how big the differential reddening is. Again, a plot showing all 15 HR diagrams. I think blinking HR diagrams is the best way to show there are differences in age. You can see how the stars are jumping up and down. Well, the whole sequences are jumping up and down, depending on the age. So the oldest cluster I found is this one at 21 million years. So I didn't cluster Orion Nebula clusters, so that my youngest clusters are about 6 million years. So maybe 10% error bars on Orion OB1A, maybe 20% elsewhere. What I call NGC 1788, that's probably Orion X. I thought I observed NGC 1788, but it's Orion X. But moving to the important part, how to get chemical abundances. So we have some data from the GLASS survey. However, GLASS survey is a magnitude-limited survey, observes only stars between magnitude 12 and 14, which translates into mostly A stars. We want to have like F, G, K stars to get good chemical abundances. So we did a dedicated survey, about 8 nights spent on Orion. Unfortunately, the weather could be better, so but we still get some results. We do have a bunch of procedures to derive ages in the GLASS survey. However, if you want to do chemical abundances, if you want to do precise chemical abundances, you might want to do something more elegant. So I did something I call Bayesian abundances, where in each step of MCMC, I generate synthetic spectra and try try to get them to fit the observed spectra. Obviously, this is terribly slow, so there are a few tricks used to actually make this happen. But at the end, you get marginalized abundances for about 20 chemical elements, marginalized over effective temperatures, log Gs, and such. All right, so one example why just glass spectra are not good enough. Stars are too hot. You don't get any spectral lines, so nothing to feed the chemical abundances. These are the actual spectra that we use. So we cover about 1,000 angstroms, about 28,000 resolving power. This makes spectra with 16,000 pixels. So that's a tough job to fit with MCMC. But yeah, this is a very typical spectrum that we have. All right, let's move to some results. I hope you're familiar with violin plots. If not, ask now because there are a few more coming. But what you have here is, in this case, distribution of metallicity. Since I have Bayesian, metallicity and abundances, I plot probability and density functions, not data points. So we can make very good measurements. So typical uncertainty is 0.014 dex. Metallicity spread all over the Orion is 0.04 dex. I can plot alpha abundances, very similar individual uncertainty, about 0.02 dex. They fit in within 0.05 dex. But what's the interesting plot is if we order these clusters by age. The bottom now we have age between 6 and 21 million years. Now, if there was any chemical enrichment from supernova type 2, supernova type 2 produce alpha elements, we should see younger groups here on the left have higher abundance of alpha elements. However, we cannot see any inhomogeneities above 0.03 dex. Just for orientation, 0.03 dex is a pollution that can be produced by maybe one big supernova or maybe three normal or small ones. If you run a statistical test on this, technically it says there are some inhomogeneities. The interpretation at these low differences is very hard because this can also be explained just by stellar evolution. So it's not necessarily primordial inhomogeneity if it's even real. Let's look also at some individual elemental abundances. I don't have time here to show all of them. Couple of alpha elements, so same story as I said before. A little bit of inhomogeneities, but no obvious pollution from supernovas type 2. Now the iron peak elements, they are most homogeneous. We also observe a lot of them. Again, pretty much no inhomogeneity that we can observe here, but this is basically expected. Surprisingly, we see some inhomogeneity in S-process elements. We do only observe 3 of them, and they're pretty tough abundances to derive. Again, I have no good explanation why we would see inhomogeneities in S-process elements. So it's quite possible that this is not even real. And I'll finish with a slide when I list everything I did not talk about, but I would be very happy to discuss later. There's a lot that goes into precise chemical abundances. Obviously, 10 minutes is not enough for this. But yeah, if you have questions, I have some extra plots about. These are mostly problems, as you see, that I have. But I think I have a solution for most of them.
Thank you very much, Janis, for your talk.
Thank you.
Yeah. So while we are waiting for, there you go. We have a question from Jan Holbert. And Jan is asking, about the age trends in these abundances. Have they been seen anywhere else, or has that not been possible?
So we do see age trends when we look at field stars, but there we don't know which population of stars actually chemically enriched that population that we observe. That can only be done in young star-forming regions, I think. So no, we have never seen something that we were looking for in Orion. Who is muted?
I am muted. Sorry. I was saying that we are running out of time, so I will move on to the next speaker. And I wanted to remind everyone that we can continue discussing on the YouTube chat window and on our online forum. So our next speaker is Aidan McBride.
Hello.
Hello, Aidan. So Aidan is from Western Washington University.
Okay.
And he will be talking to us about young runaways in Orion Nebula with Gaia. So, all yours.
One moment while we deal with the delay here.
Please close your YouTube video.
Sorry, he just ran out the door with it. All right, sorry. Thank you very much. So my name is Aidan McBride. I'm an undergraduate at Western Washington University, and I've been working with my advisor, Dr. Marina Kunkel, to identify young runaway stars in the Orion Nebula using the most recent data release from Gaia. It's well known at this point that about 50% of solar-type stars we observe have one or more companions. These exist typically in binaries or sometimes in hierarchical, stable, higher order systems. However, especially earlier in their lifetime, some of these higher order systems with 3 or more stars will be orbitally unstable. And in these cases, you are likely to have either a, typically some type of ejection event. As a simplified example, we have a 3-body system where the lowest mass component, the so-called runaway, is ejected at a fairly high velocity with respect to the other 2 stars. With a good proper motion survey like Gaia, we can project these proper motions back and try to find something about the source of origin for the runaway star. This is something we were really excited to do in the Orion Nebula, because in the environment of a young star-forming region, it can give information about the configuration of these young stars with respect to one another as they're forming, and also to just give us some information, try to constrain the frequency of these multiple body decay events. Runaways have been known towards the Orion Nebula for a while now, and Orion in general. Historically, a lot of these have been massive and very luminous stars just because it's much easier to have good proper motion measurements for them. A good example is the pair Mu Col and AE Aurigae, which are thought to have projected through the Orion region about 2.5 million years ago. Another one which got a lot of attention yesterday is in the neighborhood of the BNKL region. Source BN is thought to have passed through at high velocity and triggered explosive outflows from source I, as well as potentially triggering other runaways from this region as well. Now, in the past 15 years or so, with better imaging techniques and radio interferometry, there have been some efforts to find runaways with much lower masses, such as Kugel et al. 2017 found these 3 low mass runaways, which originate pretty cleanly back with the Trapezium region of the Orion Nebula. In the ONC, we typically think of the ONC as being dynamically cold, just meaning that the velocity dispersion of the cluster is more or less aligned with the velocity dispersion of the gas itself. However, it is also apparent that both in the radial velocity as shown here and also in proper motion space, while most of the cluster follows fairly consistent velocity dispersion, there are always going to be some outliers. These would be our potential runaway candidates. And again, this is something that Gaia has allowed us to have a much better view of the full field of proper motions that we really have not been able to see before. With that being said, we do also need to have some idea of the cluster membership before we start applying our Gaia proper motions. And to that effect, we have applied or we have compiled a catalog of Orion A membership from 22 independent surveys. We think should be relatively complete of all known members up to this point. These sources which we drew from use the presence of protoplanetary disks, their lithium or H alpha signatures, their X-ray properties that would be indicative of a young stellar magnetic field, if they have low surface gravities or high bolometric luminosities. And the catalog, fully brought together, had about 6,000 stars, although we made some spatial cuts to look at only the ONC, and our Gaia cross-match eventually brought that down to about 4,300 stars. We expect from the accuracies of our sources that there would be about 1 to 2% contamination from main sequence background stars. I think for most cases, this would not be a big deal. However, in our case, we found that the high proper motion sources in the Orion Nebula, if you're only looking at their proper motions, look a lot like sources in the background with just random velocity dispersion of their own, as shown here. This is after we have applied our proper motion cuts. And it's pretty apparent that there is a good population up here in the pre-main sequence, but there's also a population that pretty nicely defined the main sequence down here. That is the contamination that we wish to exclude. So to further make sure that we're only looking at young stellar members of the Orion Nebula cluster, we make a further photometric cut to eliminate all these, and we are then left with 26 candidate high proper motion stars. We would like to find a source of origin for these stars now that we've identified them. So we simply apply a backwards projection over a timescale of 1 million years against the field of relatively stationary O and B stars, simply because there are way too many low mass stars and potential chance alignments, which we found probably do not have a major effect. Now, not surprisingly, a significant portion, 9 of our high proper motion sources, project to the Trapezium region of the Orion Nebula. Again, the Trapezium is a very dense clustered member, or not clustered, but dense grouping of very massive stars. And it makes sense that it can give rise to many of these high proper motion stars that we expect. Of these sources, the most interesting were these two. Especially the fact that the 1961 Ori on the right is a known runaway from Kunkel et al. 2017, and also a known spectroscopic binary. And they both appear to have been ejected in a very similar event, if not the same event, about 100,000 years ago. We would be interested to see if these two are traveling in some gravitationally bound configuration or simply following similar paths of motion. Outside of the Trapezium, we are able to find 5 of our high proper motion sources that interact with other O or B stars in the field of the Orion Nebula. Again, the regions around these O and B stars should be gravitationally dynamic enough with their own companions and such that it makes sense that these would be giving rise to these high proper motion sources. Of particular interest, we found that the region around Iota Ori, which I think is NDC 1980, gave rise to 3 of these 5 sources, which we thought was potentially interesting, including one source, we have it labeled as K, interacting directly with Iota Ori itself. What was potentially a little more complicated is that we found a fairly significant population of our runaway stars appear to be randomly scattered from neighboring star-forming regions, not necessarily from the ONC itself. These yellow arrows are to show the relatively small paths of motion of neighboring star-forming regions over the projection timescales. Sources O and P both seem to originate from the OB association in Orion's belt, and the rest of these that are shown appear to come from somewhere in the region of Orion D, including this source here coming from the neighborhood of 25 Ori. Of the remaining 5 sources in our high proper motion sample, we were not able to come up with any definitive point of origin. That is likely because we were looking at very massive projection sources, but it is possible that their proper motions were simply excited by the decay of a lower mass multiple body system or some other mechanism. Of potential note of these is source Z, which is the highest velocity star of our entire sample, with linear velocity of something to the effect of 25 kilometers, sorry, not 25, 55 kilometers per second. So just to summarize, out of a catalog of about 6,000 confirmed Orion A members that we compiled, we were able to find 26 definitive young stellar runaways from the ONC, and came up with a potential source of origin for most of them. The fact that most of them projected back to either an association of very massive stars, an individual massive star, or a neighboring massive star-forming region is probably consistent with the fact, or with our expectation, that the orbital decay of a fairly massive system would be the primary cause of these outlying proper motions. And an important caveat is the fact that we were very lucky to have a good knowledge of cluster members in the ONC, but to apply this to neighboring regions in Orion or to other star-forming regions, we would really have to have a robust membership knowledge of these regions before we can really start to do similar analysis. I will leave it there and take questions.
Thank you very much, Aidan, for a really nice talk. We have one question from the audience, from Gilberto Gomez. Sorry, wrong one. More questions are coming in very quickly. So his first question is, in the hierarchical collapse scenario, peripheral star formation sensors would also yield young objects with large velocity. Can your observations distinguish between these two scenarios?
I will defer this to my advisor.
Well, it depends on the exact speeds which could be suggested by the thermal collapse. It may be possible, but I suspect that the speeds that we have are in excess of 10, 20, 30 kilometers per second. So I think that will be fairly unlikely.
Okay. And he also commented next that in the other case, the runaway should be somewhat older than the cluster they went to.
Yeah, that would definitely be the case. Which ages is something that we're looking into in a different sense, but yes.
Okay. Question from Andrew Winter. For the stars without an obvious origin, is it possible that a higher order multiple decays twice or more, computing the origin?
Can you repeat that? Sorry, our audio quality is not great.
So for the stars without an obvious origin, is it possible that there are higher order multiple that decay twice or more, computing the origin?
Yeah, that would definitely be a possibility. And also, we do not necessarily, we can't constrain that. Some of these could have come from, just been particularly lucky and come from a lower mass decay, which we would not have identified because in our earlier attempts, we found that there's just much too dense of a population to really distinguish for the especially low mass runaways. So we had to selectively look at higher mass stars as the points of origin.
Okay. Next question from Eleanor Azari. What is the distance of the candidate runaway stars? Is that consistent with the ONC, for example?
In this case, yes, we did we have checked all of their parallaxes to be consistent with the ONC.
Okay, and the last one from Carla Ramirez. From your hyperpromotion sources, which are the least massive ones?
L? Okay, yeah, source L, which would be, I do not know if I have listed it here, but I have it in a grid here. So something going back to the NGC 1980 region.
Okay, excellent. So we have no further questions. I want to thank you again, Aidan.
Thank you.
Again, we can continue the discussion in our forum, and we're now moving to our next speaker, and Konstantin Getman. I apologize, you should have spoken before. So Konstantin is from the Pennsylvania State University, and he will be talking about Gaia stellar kinematics in the head of the Orion A cloud. Please go ahead.
Thank you, Paula. Thanks a lot for this opportunity. So this talk is based on our recently published MNRAS paper with the same title, Gaia stellar kinematics in the head of the Orion cloud, runaway stellar groups and gravitational infall, by Getman, Feigelson, Kuhn, and Garmeier. So first, clusters expand at some point of the evolution. Here, from our X-ray infrared Mystic Sphinx projects, we provide indirect evidence for this expansion. For instance, is this correlation, positive correlation between cluster radius and age. As well, we find correlation between, negative correlation between cluster density and age. In Gaia era, our recent paper by Kuhn 2019 shows that 75% of clusters have a dynamical state of expansion with positive median velocity outward velocities. So with regards to ONC, situation is more complex. Kuhn suggests mild Gaia 2D expansion in the inner ONC, as shown here in this graph with a bit of positive median outward velocities. Whereas Kim shows no signs of 2D expansion in the central ONC, and Konkel suggests random 3D stellar motions in the inner ONC with slight preference for expansion in the outskirts of ONC. So no clear contraction of stellar groups was reported in this latest papers. Meanwhile, we do know that in Orion, A stars mimic the motion of gas following Forest 2008. And here I reproduce velocity versus declination diagram for the head of the cloud, where we take the recent data, radial velocities from Konkel combined with Tobin, and gas velocities from Karman Rao by Kohn. And you can see that stars, this is a red regression line, and gas, black regression line, are indeed in a good agreement with each other. And so further, considering empirical indications of gas infall in OMC1 by Hakar, and theoretical predictions of gas infall, for instance, by models of Hartmann et al. And Vasquez Medani et al., one would expect have dynamical contraction of stars in this region. But meanwhile, previous slide shows no contraction. So thus we embark here on a mission trying to search for contraction or stellar contraction in this region. Serendipitously, we also discovered a few outlying stellar groups. So we used here a rich optical infrared X-ray selected sample of young stars in the Orion A, matched it to Gaia DR2, we matched it to radial velocities from Konkel and Tobin. That resulted in about 1,500 young Gaia stars across the entire cloud and 1,700 stars with radial velocities across the head of the cloud. Important to mention that Gaia sample was considered in two flavors, full sample and restricted sample, depending on the filter on the sum of BP plus RP flux axis. But at the end, both samples showed qualitatively similar results. So to the right, what I show is the main stellar structures that we considered in our analysis. First of all, from the previous velocity position diagram, it's obvious to choose main four structures associated with the backbone, OMC23 red, OMC1 green, OMC4 blue, OMC5. And in addition, those groups with peculiar kinematics include NGC 9077 main, NGC 9077 south, two groups in extended Orion nebula here, northern group and southern group, and group X to the west of the cloud, as well as two large sparse groups. We call them western group and eastern group to the west and east of the head, respectively. And another important point to mention that kinematic analysis was done in the rest frame of the star center in the head using Cartesian XYZ coordinates with XY as orthographic projections of minus right ascension plus declination, respectively, and Z directed along the line of sight. So this slide shows how we identify stellar groups with peculiar kinematics. We used a few different types of diagrams. Two of them are shown here as an example. In the left, we show adaptively smoothed maps of distance and velocities across the entire head. And in the right hand, we show velocity position diagrams. So, for instance, in the adaptive smooth maps, it's clearly seen that, for instance, this east large sparse group has absolutely different velocity than the west sparse group. For instance, from the VI diagram, we can see that the NGC 9077 stars have definitely abnormal motions compared to the backbone of the cloud. EON groups also have here the of abnormal motions and so forth. In the right, in the velocity position diagram, another important point to mention is those black lines, solid black lines, here, for instance. These are statistical local regression feeds. We call them log feed trends, and they characterize bulk median motions of stars in the backbone of the cloud. So OMC 1, 2, 3, 4, 5. Those log feed trends are employed in our 3D stellar kinematic movies that I'll show you later. So another important point is varying line of sight distances towards different parts of the Orion A cloud. What is shown to the left is inferred Gaia distances versus declination for two permutations, full sample and restricted sample. And you can see, first of all, we recovered, of course, obviously, previous results. The tail is located at larger distances from the sun than the head. But most importantly, that distances, line of sight distances, vary across the head. You can see it's clearly. And what we find also that distances towards disky stars are systematically larger, shown here as cumulative distributions, than distances towards diskless stars, which is astrophysically expected. Also interesting to notice that stars that were removed from the restricted sample, they are not randomly distributed across the OMC1, but they rather clustered within two patches of high gas velocity associated with CO shells from Feddersen. So probably they're located in the cloud cavities or even in the opposite side of the cloud. Overall, what we find here is that head has V-shaped or shoe morphology along the line of sight, and the ONC, the central part of the ONC, thus has probably elongated sausage-like morphology along the line of sight. Another interesting result is that gas velocities anti-correlate with the Gaia distances. That was originally showed by Stutz, who interpreted it as a standing wave in the cloud. Here we interpreted alternatively as a gas gravitational contraction. And finally, I show you this 3D movie with all structures, stellar structures mentioned previously, color-coded. So the movie runs 2 million years in the past and continues 2 million years in the future. Important point is to take as those 2D summary plots from this movie. First upper plot is median distances between various stellar components towards OMC1 versus time. And the second plot is median separations between neighboring elements of the main backbone components versus time. And so clearly, main results here, if you look at this green line here, is that it shows that OMC1 stars are in a state of 3D contraction. This red line here shows that OMC2-3 stars are moving towards OMC1. This orange line indicates that NGC 9077 has tendency to depart its birthplace and move towards OMC1, whereas EON groups have tendency to depart their birthplaces and move away from OMC1. So overall, the northern part of the head show tendency for global contraction. I have briefly remind you that we've detected cohaloic gradients in numerous mystic sphinx clusters, including Orion Nebula cluster with younger core, stellar core, and older halo. And taking this all into consideration, Koch-Hollow edge gradients and current kinematic results, we can feed them into the current theoretical models of star formation in RNA. And for instance, hierarchically collapsing cloud model has lots of supporting evidences, for instance, gas inflow from HACR, gas contraction from our D versus V gas plots, star contraction in OMC1 and converging motions of OMC1 and OMC23, and Koch-Hollow edge gradients. Another model that's obviously very important is feedback by OB stars. It can naturally explain effect of OB1 population on the motion of NGC 9077 on its kinematic and location. Other models are also considered: turbulent clouds, cloud-cloud collisions, slingshot model. Important to mention also that EON groups, their small-scale motions may be related to rocket effect motions from irradiated cloudlets. And a large-scale east and west sparse groups, they probably related to drifting of older stars or slowly expanding OMC halo. So I leave you with this summary with two main results: runaway stellar groups and dynamical contraction of stellar groups. Thank you.
Thank you very much, Konstantin. We have a question from Alvaro Hakas. If you could leave your presentation up. Alvaro is asking that when you say global contraction, up to which scales are you referring to?
Contraction on the scale of cloud, on the scale of many parsecs.
Okay, thank you. And I had a question. So you're saying that you find a halo, clusters in the halo that are drifting away from the cloud, and the younger clusters are, collapsing towards OMC1. At what age do you see this difference? So the clusters in the halo are older, presumably?
Right. So eastern and western stars, we've done lots of age analysis as well, and eastern and western stars, they of about 3 million years old, compared to the backbone where Guy selected sample has an age of about 1 million years old. So the difference is about 2 million years, and if you look at the kinematics and distances, it's very likely that they originated close to a RNA cloud.
Yeah. Thank you. So then from Leiden, your talk was very well received. Apologies again for the swap. And we will continue our discussion in our online forum. If there are no other questions, we can continue there. And I would like to thank all the speakers in this session, and we are going into a break now, and we will resume with session number 8 at 18:45 Central European Time. Thank you. Bye.